Hey folks, it's Mr. G again. What we're going to be doing today is our last review video. So this is for final test in Tech 101. So what we're going to cover is a quick review of the last part of the course. I've already done review videos for the first third and then the second third. You can find those still on YouTube. And the links are still in your Blackboard. For the final test, stuff that's going to be covered. Now, the final test is all-inclusive on everything that we've done in the course. Everything from the introduction into what is electricity, to resistors, Ohm's law, series parallel combinations, maximum power transfer, and everything afterwards. All that stuff you can find review videos online that I did before. So this one is just the final third of the course, and it's going to cover things like Thevenin, Nortons, superposition theory, capacitors and DC, and an introductory into the AC waveform. So that's what we're going to cover in this particular video. Again, your final test is on everything in the course. So you'll have to go back to those other review videos to take a look. The first thing is we're going to cover is Thevenin. So Thevenin's is a theory to take a complex circuit and make an equivalent circuit, and it's equivalent with respect to the load. So if I take a complex type circuit that looks like this, and I say that this is the load resistor, the Thevenin equivalent will simplify a circuit down to something like this, or that's the load resistor, this is Thevenin's voltage, this is Thevenin's resistance. And these circuits are equivalent with respect to the load. So that means that in the original circuit, the current going through the load will match this circuit's current going through the load. The voltage that appears across that load will be the same as the voltage across that load, and the power generated in that load will be exactly the same as the power generated in that load. So Thevenin's is taking a complex circuit and making it something simple with a simple power supply and internal Thevenin's resistance, and then the load comes directly over. Now, the procedure. There are videos that I have posted for this topic. There's examples and everything, so I'm not going to actually do an example, but what I'm just going to do is run quickly through the procedure. So if we are finding Thevenin's resistance, we're going to remove the load. And why are we removing the load? Because the load gets put right down in here, and we are simplifying the rest of the circuit. So since we're not actually simplifying the circuit with the load in it, we must remove the load. I recommend that you mark it AB. So where you remove the load, mark it AB. So what that looks like is if I take that same circuit like that, where this is the the load, I'm removing the load, so getting the load out of the circuit and marking AB where the load used to be. The next step is to short the source. So we're going to short out the source. So we're going to find and replace the short right there. And now you're going to find the resistance from A to B. So find RAB, and that is Thevenin's resistance. So you get rid of the load, take the load away, mark it A, B, short out the supply, and find the resistance from point A to point B, and that resistance is Thevenin's resistance. When it comes to finding, we'll do that here, Thevenin's voltage. Thevenin's voltage and Thevenin's resistance have nothing to do with each other. They are completely separate procedures. So you start at the beginning again and you remove the load and you mark it A, B. So again, you remove the load. So now we're looking at something that looks like this. Mark it A and B. Then in this circuit, you're going to find the voltage from A to B, and that is Thevenin's voltage. So you're going to find the voltage from A to B, and that equals Thevenin's voltage. Once you have Thevenin's resistance, Thevenin's voltage, you put them into Thevenin's circuit. And again, there's examples that I've already created that are sitting in your Blackboard as video links. Norton. Norton is very similar to Thevenin. The idea is to take a complex circuit and what you're going to do is you're going to create a Norton's equivalent. Norton's equivalent is representing this circuit with a current supply instead of a voltage supply. So very similar to the Thevenins, there is a Norton's procedure. And if you're going to calculate R Norton, well, R Norton is exactly the same procedure as R Thevenin. So again, you're going to remove the load. You're going to mark it A and B for reference. You're going to short out the source. And then you're going to find the resistance from A to B, and that resistance is Thevenin's resistance, which is also Norton's resistance. Once you do that, you need to find I Norton. So finding I Norton, you're going to remove the load, and then you can mark it A and B, and then you're going to place a short, so that's a wire, between A and B, and find the current in that wire. And that is I Norton. So in this example, we remove the load, mark it A and B, then we replace the load with a short, and then what we do is we find the current through that short, and that current is Norton's current. So what you're going to do is you're going to take Norton's current, Norton's resistance, and put them into this circuit here and create Norton's equivalent circuit. There is an easy conversion between Thevenins and Nortons. So if I take a circuit, Thevenins, this is R Thevenin, V Thevenin, and load. And I want to convert this into Norton's circuit. Here's the load, here's Norton, and I Norton. So if I'm going from Thevenin's to Norton's, all I do is I take the circuit from a series circuit and put it in parallel. R Thevenin goes right to R Norton because they are the same. The load resistor goes right to the load resistor. So all I'm doing is converting series into parallel. So now what I need to do is I need to calculate I Norton. So if I have Thevenin's circuit and I want to create Norton's, all I need to do is switch it to a parallel circuit and calculate I Norton. I Norton is equal to voltage Thevenin over resistance Thevenin, Ohm's law. So if I'm given this circuit and I want to convert, I move the resistors into parallel and then I calculate the current. If I was going the other way, if I was switching from a Norton circuit into a Thevenin circuit, I go from parallel, I put the resistors in series, and then all I need to do is calculate V Thevenin, and V Thevenin is equal to I Norton times R Norton. Again, Ohm's law, Ohm's law. One simple calculation in order to go from Thevenin's to Norton's or Norton's to Thevenin's, and then all I have to do is change the configuration of the circuit. Again, there is a full video on that online. Next is superposition theory. Superposition theory is a theory that we use when we are calculating currents through a circuit when we have more than one power supply. So let's pretend I want to calculate the current through this resistor. I have two power supplies that are feeding that resistor. Superposition theory looks at each power supply separately, and then whatever current is created from this power supply is algebraically added to this one. So that means that there could be negatives involved depending on how we do it. So in this particular case, what we would first do, we're going to look at voltage 1. So we would create the circuit based on voltage 1. So for superposition theory, we focus on one supply and then we have to get rid of the other one. If it is a current supply like this one, current supplies, you leave them open. So that means that you just get rid of them. And now you're going to calculate the current that is flowing through the circuit with just one power supply. Once you have that current done, then you're going to focus on the other supply. So on the other supply, we have to get rid of this one. If you're getting rid of a voltage supply, you actually short it. So that means you replace it with a line. And now, from this supply, you're going to find your currents. So if we're looking for the current through this resistor, from this supply, it's this current. From this supply, it's this current. If the two currents are going in the same direction, you add them. If the two currents are going in opposite direction, you subtract them to find out what the net current is flowing through a resistor. So again, superposition theory is used to calculate currents and voltages and things in a circuit when you have more than one power supply. So what you do is you focus on one power supply at a time, and then you get rid of all of the other power supplies in the circuit. If the other power supplies are current supplies, you leave them open. If the other power supplies are voltage, you're going to short them. So if you leave it open, it looks like this. If you're going to short them, it looks like this. And then you're going to figure out what the current is in each case. Look at the currents flowing through the resistors you're interested in. If those currents are going in the same direction, you add them. So in this case, that current's going this way, this current's going this way. So through this resistor, both currents are going this way. There's that one and that one. So those currents would be added. If those currents were going in opposite directions, they would be subtracted to find out what the net current is through each component. And that's superposition theory. Again, there are videos and examples on your Blackboard site. And they're also permanently sitting on the YouTube site. Capacitors in DC. So capacitors take on a couple of different looks for their schematics. We have what they call electrolytic capacitors. Those ones have a polarity, and then we have a non-polarized capacitor. So electrolytic capacitors have a positive side and a negative side, so they have to be put in a circuit properly. The unit is the farad, and that's the unit of capacitance. Many of the capacitors you're going to see have something like 10 microfarads or 0.1 microfarads. What a capacitor does is it stores a charge. In DC, think of a capacitor as a small little battery, and it'll store a charge for you to use later on in your circuit for something. The amount of charge stored is given as the capacitance. So you'll see the capacitor value is equal to, again, let's say 100 microfarads. You'll also see a voltage DC rating on a capacitor of 16 volts. And what that means is that capacitor can handle a maximum amount of voltage of 16 volts. So from one side to the capacitor, so it can be charged up to a maximum of 16. If we apply a capacitor in a simple little circuit, so let's say 10 volts, 100 ohms, 10 microfarads. This becomes a charging circuit. When current flows, current will flow through the resistor and into the capacitor. Eventually, the capacitor will start to build up a charge, and it will stop when it has reached the equal value here. So it will stop at 10 volts. So the full charge on this capacitor would be 10 volts because that's what the supply is. How much time does it actually take to charge a capacitor is based on two things. One is the size of the capacitor, which is C, and the other is the amount of current allowed to flow, and that current is controlled by R. R times C is what's known as the time constant, tau. So a time constant is a factor of the resistance in the circuit and the capacitance in the circuit. In order for a capacitor to go from zero or empty to full charge, it takes 5 tau. Now a tau's unit is in seconds. It's a measurement of time. So in order for the capacitor to be charged from 0 to 5 tau, or to full charge, it takes 5 tau. There is a charge curve for a capacitor. And this is a standard for all capacitors. The charge curve looks like this. This is voltage, and this is time, and basically looks like this. It's a logarithmic graph. And if this is full charge, this amount of time is 5 tau. If I divide that 1, 2, 3, 4 tau, 1 tau, you get up to 63% full charge. Two tau is 84%. 3 tau is 95%. 4 tau, 98%. And 5 tau, you're at full charge, which is 99% or above. So after 1 tau, 2 tau, 3 tau, 4 tau, we can figure out how much percentage is actually left, or how much has been charged in that capacitor. This graph is created by this formula. Voltage on a capacitor is equal to final voltage plus the initial voltage minus the final voltage, E to the minus T over tau. So basically you apply this formula and it will give you the charge on the capacitor at any moment in time. So this is time. Tau is R times C in the capacitor, or in the circuit. E is natural log, which is what creates this particular graph. This formula is on the formula sheet for the course that we've been using all along. It is the final formula on the sheet, which is right there. If we are discharging a capacitor, the discharge curve looks exactly the same, only opposite. So, after 1 tau on the charge time, I gain 63%. If I'm discharging the capacitor from full, on the discharge, I'm losing 63%. So what I have left is 37%. And the same thing goes for the rest. 2 tau, on the charge time, 2 tau is actually 84%. So therefore, on 2 tau on discharge, I lose 84%, and what I'm left with is 16. Why do I think that's 86%? Now that I'm thinking of it, I think that's 86%, and that would be 14. There we go. That looks better. So, 3 tau, I either gain 95 on a charge or I lose 95, and what I'm left with is 5. You get the picture. This is your final value. This is your initial. This is your final. So if we are charging, the final value is full charge, so that would be, in this example, 10 volts. The initial is 0 if we're starting it empty. Final 10. If this is discharge, my initial is going to be 10, because I'm starting full charged, and my final would be 0. So again, 1 tau 63%, 2 tau 86%, 3 tau 95%, 4 tau 98%, 5 tau 99%. And last but not least, intro into AC. In the video for the lesson, you can see how an AC waveform is created. So we end up with something that looks like this. There's some important values in here that you need to know. This is the positive peak. This is the negative peak. The difference between them is known as the peak-to-peak voltage. The time that it takes for one cycle is called the period. And the number of cycles you get in 1 second is called the frequency. So the frequency is equal to the cycles per second. And the unit for that is called the hertz. So period is a measurement of time. Frequency is a measurement of how many we get in 1 second. So the period, the amount of time, is equal to 1 over the frequency. Therefore, the frequency is also equal to 1 over the period, or the amount of time. There are 2 voltage points that are in particular importance to us. There's one here which is 0.637 times the peak. That's what we call the average. So the average of the waveform. And basically, if you look at a sine wave, the overall average is 0 because I got the same amount above and the same amount below. This average is actually the average of half the waveform. So it's the energy that is produced on half of the waveform. So this is the average energy. And then last and most important is this point right here. And that point is called the RMS value. And that value is 0.707 times the peak. An RMS value RMS stands for root mean squared. And basically that's the formula on how this was derived, root mean squared. So let's say I had a peak value of 10 volts. If I take that 10 volts and I square it, and then the mean is that middle point, divide by 2, and then the square root, this is actually 7.07 volts. So if I have a 10 volt peak, I square it, divide by 2, and take the root, I get 707. So this is how this 0.707 times the peak is derived. So that's what it stands for, but what does it actually mean? RMS value of voltage is an equal power point to DC. So if I had a DC circuit and I had 120 volts and a 40 watt light bulb, when I hook up that 120 volts to that 40 watt light bulb, I am going to get a certain amount of brilliance out of that light bulb. If I want the same amount of brilliance out of the same light bulb, but in an AC system, again, the equal power, so 40 watts with the same brilliance, I must set the voltage to 120 volts of RMS value. So that means that if I set the AC waveform to 120 volts of RMS, I will get the same amount of power delivered to the load as if I was doing it with a DC supply. So what does that actually look like? Well, if we go back over here, that means that this point right here is 120 volts. So that means the peak on my waveform is actually going to be 120 divided by 0.707, and it's going to be something like 169.7 volts. So when I apply my waveform, it will have a peak value of 169.7 volts, which gives me an RMS of 120, which would match the power here. So it's an equal power point between AC and DC. So that gives you an overview of the last third of the course. Again, there's more details and examples and things like that in your full videos. So again, the other videos that I did, review for test 1, review for test 2, this is the final test review. So this one covers Thevenin's, Nortons, and the switching of back and forth, superposition theory, basics of capacitors in DC, and an intro to AC. Now, one thing that I did not mention in the capacitors one is what happens when you have more than one capacitor in the circuit. So let me go back here. So what happens if I have capacitors in series? Or if I have capacitors in parallel? And I want to find the total capacitance. You already know the formulas. They're exactly the same as the formulas for calculating resistors, but backwards. So the formula for calculating capacitors in series is the same as the formula for calculating resistors in parallel. When I have capacitors in parallel, the formula is exactly the same as resistors in series. And these formulas are also on your formula sheet near the end. So, capacitors in series, you use the same formula as resistors in parallel. Capacitors in parallel, you use the same formula as resistors in series. So that should give you a good idea of what was covered in the last third of the course. Again, if you're looking for more detailed videos, they are online. There's a video for every single topic that we covered, and the links are still there in your Blackboard. So, good luck on your exams, folks. Take care.